So far, we've been talking about water and solutes, and we discussed how with hydrostatic pressure, water moves from an area of high pressure to an area of low pressure. So our blood, which is mostly water, moves from high pressure arteries into low pressure veins to return to the heart. But there's another concept we have to understand. Sometimes water doesn't move with pressure. There's another force working on it. And that other force is called osmosis. Osmosis is the concept of water moving through semi-permeable membranes. In this case, the water will diffuse through the semi-permeable membrane, and it's going to go through that membrane in order to reach an equilibrium. Water molecules like to have the same amount of water molecules on either side of the membrane. So this is water diffusing through a semi-permeable membrane to reach an equilibrium with itself. However, this membrane is semi-permeable. Water is free to move through this membrane in any direction, but the solutes are not. They're too big to go through the membrane. And so if there's a concentration difference between the two sides of the membrane, called a concentration gradient, a difference between the concentrations on both sides of that membrane, then water will be drawn to the side that has less water in it. If there's solutes dissolved in the water, then where those solutes are, there's no water. So there's less water on the side that has lots of solutes. So water will go through the membrane to reach an equilibrium, and water will also move toward the liquid that has more solutes in it. The liquid that has more solutes in it has less water in it. Those solutes take up space. So water will move through the membrane, because it can, to reach equilibrium on both sides of the membrane, pushing those solutes out of the way until water is equal on both sides. The solutes can't go anywhere. They're stuck on their side of the membrane. So only water is moving in osmosis. To demonstrate the concept of osmosis, I'm going to use an egg. You know that an egg is combined two things: the egg yolk, which is surrounded by a membrane, and the egg white outside of it, which is also surrounded by a membrane. And that membrane is semi-permeable. When you break an egg, you can see that membrane as that white stuff you try to keep out of your recipe, that thin, filmy layer that surrounds the egg. To do osmosis, I need to remove the shell from these eggs so that we can see the semi-permeable membrane that lies beneath. So to do that, I'm going to take this egg and put vinegar on it. The vinegar is an acid. The shell around the egg is a base, mainly made of calcium. I'm going to let this egg sit in here overnight, and that shell will dissolve from that egg, leaving the egg yolk intact, the egg white intact, and the membrane around that egg white all intact. So I'll now have a semi-permeable membrane with the egg white in the inside and whatever I want to put around the outside when I put that egg in there. So right now it's going to sit in the vinegar overnight, and our shell is going to start disappearing. In fact, I don't know if you can see it, but there's actually little bubbles coming off of that shell, giving us the beginnings of that shell dissolving. That calcium will dissolve into the vinegar and make the vinegar a little bit cloudy by tomorrow morning. Here you can see some of that eggshell already dissolving into my vinegar. Okay, here we are the next morning, and we see that some of the calcium has come off the eggs. You can see this, but I can now squish the egg, and you can just see that when it's all done, all I'll have is the egg white showing, and all this white stuff will be off. Okay, now you can see that one egg is almost done, and the other one still has a bit of shell in it, so I'm going to put more vinegar on it and let it sit some more. Okay, so the eggs have been sitting in vinegar overnight, and we're about to find out that vinegar is not a solution full of a lot of things, because look what happens to our egg. Okay, as you can see, the egg on our left, which no longer has its shell on, is slightly larger than the egg in the middle, which still has its shell on. So if we think about it, the egg is surrounded by a semi-permeable membrane, and it was sitting in vinegar, which is mostly water. And we notice that the egg gets bigger. So the egg white must have been hypertonic, meaning the egg white had more solutes in it, and the water, which was hypotonic, or less solutes in it, and the egg that was hypertonic with more solutes drew the water into itself. So the water moved towards the area of more solutes. In this case was the egg white area. I've had the other egg sitting in Caro syrup, which is a very hypertonic solution. And you can see already that the egg has gotten smaller. The egg white this time, though it has a lot of solutes in it, has many more solutes in it. The syrup has many more solutes in it than the egg white. And so the water was drawn into the syrup away from the egg, making the egg smaller. So the egg white here on the right shows fewer solutes and is hypotonic as compared to the syrup solution, which is hypertonic and has more solutes. So the water in the egg thus went towards the syrup instead. Okay, let's take a look at our eggs this morning. We can see the egg that was placed in water has grown considerably larger. And voila! The egg that was in syrup last night has pretty much turned into an egg yolk with a bag around it. You can see this. There's almost no water left in that egg white whatsoever. And the syrup has turned quite runny. So, in osmosis, we have water moving towards solutes. In this first egg, the egg white contained solutes, way more solutes than the water did, and so the egg absorbed the water. In this egg, which was surrounded by syrup, the egg white had solutes in it, but not nearly as many as what was in the syrup. So the water left the egg and moved towards the syrup. This egg was hypotonic compared to the syrup, which was hypertonic. Water moves towards the hypertonic solution. Thank you.